Hello, so this is the second Zoom meeting on chapter 7 review part 2. So this part is more on reaction types, and we've answered question 1 and 2. And we are arrived at question 3, which is asking you to balance the following redox reactions. Which reactant is oxidized, which reactant is reduced, and write the half reactions, the corresponding half reactions. So let's see what it means as we do it. First, we want to balance the redox reactions. So you're told it's a redox reaction. Let me make this bigger just to make sure this is visible enough. Oh, wait, not this. Okay. So yeah, the question is above here, but the equation is below on the second page. So let's balance. We have 1 Cu on the left, 2 Cu on the right. So let's make it 2 by having a 2 in front of the Cu on the left. And that means here a 2, and let me make it red so we see it. So this way we have now 2 Cu on both sides. Oxygen, we have 2 oxygen on the left, 1 oxygen on the right. So we want to make it 2 oxygen on the right. So we will make a second coefficient of 2 here to make it 2 oxygen on the right, just like we have on the left. This unbalances the coppers. So we will actually need to rebalance the copper. And so 2 times 2, we have 4 coppers on the right. So let's change that 2 that we had in front of Cu on the left. Let's make it 4. So now if we recapitulate, we have 4 copper on the left, 2 times 2, 4 copper on the right. 2 oxygen on the left, 2 oxygen on the right. So this is balanced. Next, we need to decide which reactant is oxidized and which reactant is reduced. So when you have redox reactions, one of the reactant, so on the left side, one of the reactant is reduced and the other is oxidized, and we don't know yet which one. But the question is asking to answer with a reactant formula, right? Don't answer with a product formula because it would not make sense. It's asking which reactant is oxidized and which reactant is reduced. And when you found the one that is reduced, then automatically the other one is oxidized when you have only 2 elements like here. So how do we decide that? In oxidation reduction reactions, the elements may gain or lose electrons. Oxidation reduction reactions, their driving force is the transfer of electrons from one element to the other. And the element that loses electrons is oxidized, and the one that gains electron is reduced. Remember the oil rig, oil rig acronym to remember which one is which. RIG is for reduction is gain of electron, and OIL is for oil is loss of electrons. So you want to find out which one. So you want to find out what is the state of oxidation of each of the elements, on the reactant side and on the product side. So we will use the so the oxidation state of elements when they are like metals, like here copper is a metal. And if we look at the periodic table, you see copper there, transition metal. So copper is a transition metal, as you can see here, and for all metals, so which means all elements that are below the staircase here, below this line here. You know that they are all metals, right? So all the elements to the left side are metals, and when we talk about just the symbol of the metal, it means it's the metal at room temperature, it's a solid, and we say it's the element in its elemental state, right? So when you have copper in its elemental state like that, the charge is necessarily 0. So you can write above that the oxidation state for copper on the left side is 0 because it's copper in its elemental state. Oxygen is not a metal, so oxygen is there. It's from group 6A, and it's one of those 7 diatomic molecules. You know, there is nitrogen, oxygen, fluorine, chlorine, bromine, iodine, and then hydrogen. And they are made of 2 atoms bonded together when they are in their elemental state. And so for them, it's also going to be the oxidation state of 0 when it is in its elemental state. And so O2 as a gas is in its elemental state. And then the oxidation state will be 0 as well. Now we have to decide for copper and oxygen when they are in the product Cu2O. And so this is an ionic compound, right, made of a metal and oxygen, a non-metal. So in ionic compound, you just find out the ions they are, and that will tell you the oxidation state. And so in Cu2O, so oxygen is a predictable ion. So for this one, you can tell that it's going to be 2- because oxygen is in group 6A, and it makes a 2- ion always. So that's going to be its state when it's in this ionic compound. So 2- is for oxygen. And then we have 2 Cu per oxygen, right? So the 2 negative charges from the oxygen will have to be cancelled by 2 positive charges from the 2 coppers. Because we have 2 coppers, each copper will carry 1 positive charge. So the charge on the copper here is just +1. So I can write 1. So it's +1 on copper. So you can see that copper goes from Cu oxidation state 0 to Cu+. So let's write the half reaction for that. And so we will move here and write Cu in its elemental state. So as a solid, doesn't need to be, will become Cu+. Oh. And we have the arrow there. Let's insert an arrow. Okay. The plus here is superscript because it's an ion. So when copper becomes Cu+, the ion, it loses 1 electron. So when you're losing 1 electron, you want to write that the electron is extracted. So plus, and then we will show that the electron is here now, right? Because when you are losing the electron is detached from the ion. So you place the electron on the side with the ion, the positive ion. So Cu loses an electron to become Cu2+. So let's write this. Cu loses an electron to become Cu+. So if you Cu loses an electron to become Cu+, that means copper, you know, is oxidized, because loss of electron means oxidation. So copper is oxidized. So for oxygen, what happens to oxygen? So we start with oxygen as O2. the gas, so in its elemental state. And it becomes O negative 2, the oxide ion in the copper oxide. So for O2 to become O negative 2, it needs to gain 2 electrons, because you see that, from the left to the right, there is 2 extra electrons now on oxygen. So we need to add 2 electrons on the left side to show that O2 gained 2 electrons to become the oxide ion. And so that means oxygen gained electron, right? So oxygen gained 2 electrons to become O negative 2. So that tells you that oxygen is reduced in this reaction because it gained electron. We know now that reduction is gain of electrons. So that's how you decide which reactant is oxidized and which reactant is reduced, right? And you see how when copper is oxidized, then oxygen is necessarily reduced because the electrons have to be gained by the other element. So copper gave 2 electrons to oxygens, or the 4 coppers here gave 4 electrons, and the O2 here gained 2 electrons, 4 electrons, and became 2 O negative 2, right? That's what happens because we have 1 O2 here, so per oxygen it gained. Oh, hold on, I have a mistake here. Because here the subscript 2 tells you that you have 2 oxygen atoms. So you need to gain actually 4 electrons here for 2 of the oxygen negative 2. So we see that in the elemental oxygen, we have 2 oxygen atoms, and so it will split into 2 oxide ions, right? 2 oxide ions. And each oxide has 2 negative charges, 2 electrons that it gained. So that means 2 times 2, 4 negative charges. So that's why on the left side, we need to add 4 electrons, right? The oxygen as the gas has gained 4 electrons to become 2 oxide ions. So just to go back here to the text of the question. So the half reactions are those 2 half reactions we see here. That's the half reactions for the oxidation, and that's the half reaction for the reduction part of this redox reaction. Okay, so we can do the second example now. And that's with strontium plus water gives strontium hydroxide plus H2, the hydrogen gas. So you see how H2 here is in its elemental state, right? You remember I told you this is part of the 7 diatomic elements. And H2 here is in its elemental state. So we can already write that it's a state of 0 above it, an oxidation state of 0, because it's hydrogen in its elemental state. Same with strontium. Strontium is a metal, and here it's just a symbol of the metal, solid. So that tells you it's strontium in its elemental state, and its oxidation state is 0, 2. So water is a molecular compound. And when you have to find the oxidation state in molecular compound, you treat them like if they were ionic compound, in fact. So we will do like if it was an ionic compound. And when we have oxygen as an ion, you know, as we saw earlier, that oxygen will make a -2 ion, right? So that means the oxidation state of oxygen here will be -2. And then hydrogen is a +1. And you can see that with 2 H plus and 1 O minus, this will be a neutral molecule, the molecule of water. So here, each hydrogen is +1, right? What I write above the elements here is for one atom at a time, right? So the plus here is for one atom of hydrogen. So that's the oxidation state of hydrogen and oxygen in water. And then in strontium hydroxide. So strontium hydroxide is an ionic compound. So we can find out what kind of ions we have in this compound. The hydroxide ion, hopefully you recognize it's, and let me see, yeah, it's one of these polyatomic ions, and it's here. The hydroxide, OH minus. So overall, the OH together is -1. But if we do the same thing as telling ourselves that we have, atomic ions, the oxygen will be 2 minus. So let's write 2 minus above the oxygen. Then the H will be a +1. And then the strontium, we need to find out. So because the hydroxide is giving 2 negative charges to this compound, we have 2 hydroxide, so 2 negative charges, and we have only 1 strontium. So the strontium is a 2+ here. So again, the 2+ is for strontium, the 2- is for 1 atom of oxygen, and the +1 is for 1 atom of hydrogen, right? So we treat them 1 atom at a time. So that means what we have is that the strontium started as, the solid, the elemental strontium with oxidation state 0. And then we have the arrow, and it becomes the strontium 2+, right? On the right side is the strontium 2+. So where are the electrons? So you will add the electrons on the right side, because strontium to become strontium 2+, it's because it has lost 2 electrons. So you want to take away the electrons from the strontium and separate them from the ion. And so we need to extract 2 electrons from strontium because we have 2 positive charges. So that means strontium, and let's give enough room here, strontium lost, right? Lost 2 electrons to become strontium 2+. So strontium is oxidized. So that tells us that strontium is the one that is oxidized here. And so this is a 2+ here. So let's look at oxygen now. We have oxygen in its, well, not in its elemental state, but here oxygen is a 2-. And then again here it's a 2-, and there is only oxygen in those 2 reactant and product. So oxygen has not changed state. So we can say that oxygen stayed the same from left to right. Same oxidation state, or kept, maybe let me write this, kept the same oxidation state from left to right. So that's not oxygen that is reduced, right, to compensate for the oxidation of strontium. So it has to be hydrogen. And hydrogen here on the left side started as a +1. So H plus, and then it became H2 here. It also became H plus here, but we are not interested in the hydrogen that stays the same. We want to see if hydrogen becomes different, and here it becomes different. It becomes H2, which is oxidation state of 0. So that tells you here there was a change. And so H plus to become H2, so that means you need 2 H's plus, right? And they will each need to gain an electron, so plus 2 electrons will become H2, right? Because, so we need 2 H, so that's why we have 2 H plus here, because we have 2 hydrogens on the right. And each H plus will gain 1 electron to become H2. So in this case, hydrogen gained. So if we look at hydrogen atoms, you say that it gained 1 electron. It gained 1 electron to become just H without any charge. Maybe I'll write this differently and say that 2H plus. So 2H plus gained 1 electrons each to become H2. So that tells you hydrogen is reduced because it gained electron from left to right. So it's the reactant that was reduced. So that answered the question. Strontium is the one that is oxidized, and we have its half reaction here for the oxidation. And then hydrogen is the reactant that was reduced, and it's from H plus that it became H2, and that's how it's reduced into H2. Okay, so we can move on to question 4. Given all the equations above, classify them according to the following categories. So synthesis, decomposition, single displacement, or double displacement. And I have a table here showing you what is the generic equation for a synthesis. So you see A plus B gives AB. So you make a big molecule from 2 other smaller molecules. Decomposition is when you are breaking down a big molecule into 2 or more products. Displacement is when you have an element. So A would be the element plus BC, a compound, gives another compound and a new element. So you need an element and a compound, gives 2 new compound and element. And then double displacement is when you have 2 compounds and they exchange partners and become 2 new compounds. So AB plus CD becomes AD plus B or CB. So this is available in this document I made available in Canvas for you, and that shows how to classify reactions according to what atoms do. And that's the last slide here, right? So the synthesis, decomposition, single displacement, double displacement. So 1A, so you need to go back to question 1A here to decide what kind of reaction you have. So it was the reaction with rubidium hydroxide and nitric acid. Gives the rubidium nitrate plus water. And it's an acid-base reaction, right? Acid plus base gives water plus a salt. And you can see that to find the way, to find the product, we did some double replacement here. We did exchange of ions, right? Rubidium took the negative ion from the other compound, and then the H plus combined with the OH minus. So we have an exchange of partners here. And this is typical behavior for double displacement reactions. So we can write here a double displacement for 1A. 1B. Again, that was another acid-base reaction with HClO4 plus NaOH. The base gives water plus a salt of sodium perchlorate, I believe, perchlorate, sorry. So again, we see that there was an exchange of partners between the ions of each compound. The positive ion from the first compound went with the negative ion of the second compound. And the positive ions from the second compound went with the negative ion of the first compound. So there is an exchange of ions, exchange of partner. And again, that's typical of double displacement reaction. So we can write double displacement again. Sometimes it's also called double replacement instead of displacement, RE here, which is the same. 2A was HBr plus LiHCO3 gives H2CO3 plus LiBr. And we had the carbonic acid that was unstable and decomposing in water and carbon dioxide. This is also a double displacement reaction because you can see the exchange of partners again here. Lithium goes with bromine, and then the H plus goes with the bicarbonate ion. So double displacement. Then 2B. 2B was also a gas evolution reactions where you have the ammonium going in with the hydroxide to make the ammonium hydroxide, which dissociates into ammonia, and water. And then you have the K2SO4 salt. So again, here we see an exchange of partners between the ammonium and the hydroxide, and then the potassium and the sulfate. So they exchange partners, and so that's again a double displacement. So I want to emphasize that, and let's look at this for that. All the reactions that are precipitation reaction, acid-base reactions, gas evolution reactions, these three here are always double displacement reactions. You should expect that they will always be double displacement reaction. And that's actually how we find the formulas of the product. So these three will be double displacement reaction. Let's look at the redox reactions. So there you have a lot more variability into what kind of reaction you have. So here we have two reactants giving one product. So that's the key to recognize what we call a synthesis or combination, when you have two reactants or more combining into one bigger molecule. So the key to recognize a synthesis or a combination is the fact that there is only one product. So that was a synthesis because we had only one product, the Cu2O, right? Cu2O. 3B, we have again a redox reaction here, and this time we have, two reactants, two products. So it's neither synthesis or decomposition. However, you can see that we have an element plus a compound. So strontium, the element, plus water, the compound, give a new element, a new compound, sorry, the strontium hydroxide, and then a different element, H2. So we have this form of the single displacement, which shows that A plus BC gives AC plus B, because you recognize those single displacement by the fact that you start with an element and a compound, and you end with a new element and a new compound. So that was a single displacement reaction. So you see how redox reactions can be a variety of things. So let's classify these other reactions that are not always complete here. You need to balance them. So classify those reactions represented by the following unbalanced equation by as many methods as possible. And then complete the equations that are not complete and balance them. So we will start with 5A. It's this. We see magnesium plus silver nitrate gives magnesium nitrate and silver again as a solid. So let me make this bigger. So we need to balance first. So let's see. This is not balanced because we can see we have 2 nitrates on the right and only 1 on the left. So we need to make it 2 silver nitrate on the left to balance with the right. So that will balance the nitrate, because remember how when you have polyatomic ions that are, the same from left to right, they don't change, they are not broken down. Then you balance by balancing the polyatomic ion first, and it will be easier. So here we have 2 nitrates on both sides. Now we have 2 silver on the left. So let's make it 2 silver on the right. Magnesium, we have 1 magnesium on the left, 1 magnesium on the right. So it looks like that's the only thing we need to do here to have it balanced, because 2 silver on the left, 2 silver on the right, 2 nitrate on the left, 2 nitrate on the right, and then 1 magnesium on both sides. So it's balanced and complete. Now we need to classify by as many methods as possible. So that means you need to classify using this way of classifying reactions, and also using this one, the synthesis, decomposition, single displacement, and double displacement. So they have to be classified at least in 2 ways. So let's go back here. So overall, we can see we have magnesium, it's an element, plus silver nitrate, that's a compound. And then we get a new compound, magnesium nitrate, and then a new element, silver. So it is of the form, for the single displacement here, A plus BC gives AC plus B. So we can already say that it's a single displacement here. Displacement. So single displacement is one way. And then we want to classify that as either an oxidation reduction reaction, acid-base, precipitation, or gas evolution. So even though here you are making a solid, on the right side, on the product side, you're not making a solid from 2 aqueous solution, because that's how we recognize precipitation reaction. Precipitation reaction is, actually I want to stay here. You need 2 soluble ionic solutions, and you make 1 insoluble product. Here we have only 1 solution, and then the other is a piece of metal. So that's not a precipitation reaction. It is not an acid base either. And it's not a gas evolution, because we don't have a gas. So it looks like it's an oxidation reduction reaction. Oxidation reduction reaction. Let's verify by seeing if indeed the oxidation state changes from left to right. So we have magnesium on the left as elemental magnesium, solid metal. So that's an oxidation state of 0. And we can say the same of silver on the right side. It's the oxidation state of 0 here for silver. Nitrate, notice how nitrate stays the same from left to right. So we know that nitrate is not reduced or oxidized. So let's look again at silver on the left side. The nitrate is the, let's look at the list of polyatomic ions here. And you can see that nitrate is the NO3 -1 ion, right? So we have one negative charge on the nitrate. So the silver has to be +1 to compensate for that. So silver will be +1 here. And then magnesium in the nitrate compound here, magnesium will be a 2+ because we have 2 nitrates, so bringing 2 negative charges. So we need magnesium to be 2+, which fits because magnesium is, you know, in group 2A, and that's a 2+ ion. So we can see that indeed we have an oxidation reduction reaction, and let's specify which one is reduced and which one is oxidized. So magnesium goes from being oxidation state 0 to 2+. So that means it is oxidized. Magnesium is oxidized to become magnesium 2+. So that means it lost 2 electrons, right? It lost 2 electrons to become 2+. And then the other one, silver. Silver was silver plus at first, right? Silver plus in the nitrate. Silver plus is reduced to silver. Yeah, that's it. So silver plus is reduced to just silver, the elemental silver. So it gained an electron, right? Ag plus gained an electron to become Ag with oxidation state 0. So that confirms that it's an oxidation reduction reaction. Let's look at example B. So we have mercury oxide here as a solid, becoming mercury liquid plus oxygen gas. So let's find out the first type of way of classifying. So do we have a synthesis, decomposition, single displacement, or double displacement? You can see here that you start with one reactant only. So one reactant only tells you it's a decomposition, right? When you have one reactant and you break it down into 2 or more products, then that means you have a decomposition reaction. Okay, so next, we can see that it cannot be acid-base, it cannot be precipitation reaction, it cannot be a gas evolution reaction. Even though we are making a gas, it is not a gas evolution reaction, because if you're looking at the clue to recognize a gas evolution reaction, you need to start with 2 aqueous solutions, and then one of the product will be a gas. Here we start with a solid, so it doesn't fit the pattern. So this is not a gas evolution reaction either, nor acid-base, nor precipitation reaction. So it looks like it's again an oxidation reduction reaction. So let's look at the oxidation states then. We have, let's look at the right side first. On the right side, we have oxygen, the gas. So that tells you it's oxygen in its elemental state there. And we have mercury as a liquid. And you should know by now that mercury is the only metal that is a liquid at room temperature. So mercury as a liquid is mercury in its elemental state. So that means it's also a 0 oxidation state for mercury on the right side. However, in the left side, you have an ionic compound because you have a metal and a non-metal. We know that oxygen makes the -2 ion, so it's going to be a 2- for oxygen. And then the mercury here has to compensate the charge because this HGO compound is neutral. So that means mercury is a 2 plus. So mercury is 2 plus, oxygen is 2 minus. So you definitely see a change in oxidation state for both elements here. And so let's write down what which one is reduced, which one is oxidized. So mercury, Hg2 plus, it's a 2 plus to start with here. Is reduced, right? Because it gained 2 electrons to go from 2 plus, is reduced to become Hg liquid, right? So from 2 plus, it became oxidation state 0. That means it gained 2 electrons. So that's why it is reduced. So that means oxygen is actually, let's write that it's O negative 2. We start with the oxide ion here. O negative 2 is oxidized into O2. O2, the elemental oxygen gas. So you see that for O negative 2 to become O2 with oxidation state 0, that means O negative 2 has lost electrons, right? So that's why oxygen here is oxidized, because we have a loss of electrons. So next example, we have HNO3 aqueous plus KOH aqueous gives, and here we need to finish writing the equation. You probably recognize this as an acid because we have H first in the formula. So that tells you this is an acid. In an acid, the H will be an H plus. So if I write the ions, and let me write the ions below. Here. So we have H plus. And then the nitrate is the NO3 negative 1 ion. And here you recognize the hydroxide ion, the OH minus ion, and then it's with the K plus ion. So these are the ions that are making up those compounds, right? And we can tell here that there will be an exchange of ions because the positive ion here will be attracted by the negative ion of the other compound, and the nitrate here will be attracted by the potassium due to the difference of charge. So we will do a double displacement equation here and exchange partners. And so let's write the formulas of the product by following this exchange. So we have K plus, K plus, and then NO3 negative 1. The 3 is a subscript and the negative charge is a superscript. So what happens when you put them together? You can see that one positive charge will cancel the one negative charge. So you can remove the charges, and that's the formula. KNO3 is the product for this. If we do the solubility rules here, we can see that K plus and NO3 minus, here K plus, NO3 minus, they are making soluble compounds with no exception. So this is definitely soluble. So we can write AQ for soluble. And next we need to add the other product that comes from the exchange of ions from, H plus and OH minus. H plus, OH minus. You may remember from last time that when you have H plus and OH minus combining together, you're making water. So we will have 2 H and then 1 oxygen, and that's the molecule of water. And so because it's water, it's a liquid, right? It's not aqueous, it's liquid. So you can definitely tell here we have, so if we classify all of this, let me, bring this back together here. Okay. So we have a double displacement reaction for sure, because we did exchange partners. And then we have an acid-base reaction, acid-base reaction. This was the acid here, acid plus base. The KOH is the base, gives, and then we have the salt plus the water. So hopefully you recognize that general form of acid-base reaction. So this is a double displacement and acid-base reaction. Okay, so that's for question 5C. So let's do 5D now. So note, I want to go back to question 5C here. Notice how balancing was already done automatically here because one NO3 here on the left, one NO3 on the right, 1K on the right, 1K on the left. And then the H plus plus the OH minus make one molecule of water. So this is balanced. Let's look at example D. It's already written for you, the product. So is it balanced? No, it's not balanced. So even though the aluminum are balanced, we have one aluminum on both sides. The bromine are not balanced. We have 2 bromines on the left and 3 bromines on the right. So when you have 2 and 3, you need to make it 6 for both sides because you need the least common multiple here. And so that's going to be 3 bromine on the left, because 3 times 2, it's going to be 6 bromine. And then that means we need a coefficient of 2 in front of AlBr3 to make it 6 bromine on the right, because 2 times 3 is going to be 6. However, this changes the number of aluminum on the right. We have 2 aluminum on the right now. So we need to make 2 aluminum on the left by having a coefficient of 2 in front of Al. And now if we check, we have 2 aluminum on the left, 2 aluminum on the right. 3 times 2 bromine on the left, 2 times 3 bromine on the right. So this is balanced. So let's write that we balanced it here. And that's what we did in green. So now we need to decide what kind of reaction we have. The first classification here we want to look at is this one. Do we have a synthesis, decomposition, single displacement, or double displacement? And I don't know if you noticed, but we had only one product. So that looks like a synthesis. So one product here only. So this is a synthesis. Synthesis because we have one product. So that's this way of classifying. What about the other way? This way, you know, all that. So it cannot be either precipitation, acid base, or gas evolutions, because they all start with, you know, ionic solutions, 2 ionic solutions, and here we do not have that. It's a solid and a liquid. So this must be an oxidation reduction reaction. So let's verify that by seeing which one is reduced and which one is oxidized. So let's look at the oxidation states. And so again, when we have elements in their elemental state, like here, aluminum as a metal is in its elemental state. So that's going to be an oxidation state of 0 for the aluminum solid on the left. Bromine is one of these diatomic elements that makes a diatomic molecule. So it's bromine in its elemental state here. And that's again an element oxidation state of 0. AlBr3 is an ionic compound. So then we need to find what kind of ions we have there. Bromine being an halogen here makes a -1 ion. And then aluminum here, it's a metal from group 3A, and so it's a predictable ion as well, and it's a 3+ ion. So, and it confirms the formula here. So 3+ for aluminum, and then -1 for the bromine. For each bromine, right? We have 3 bromine, each 1 negative charge. So that's 3 negative charges in total that are cancelled by the 3 positive charges on the aluminum. So it is an oxidation reduction reaction. We can see that the aluminum and the bromine change oxidation state. And so aluminum at first is, the solid, and it is becoming aluminum 3+. So it is oxidized to become Al3+, right? Because to become a positive ion, you need to lose electrons. So losing electron means you are oxidized. So that's for aluminum. And then if aluminum is oxidized, that means bromine is reduced, Br. And so we start with Br, the liquid, Br2, the liquid. So bromine in its elemental state is reduced into Br minus the bromide ions. And that makes sense that it's reduced because here the bromine, each atom needs to gain an electron to become the bromide ion. So that classifies this reaction. So let's do 5E now. So we have 2 reactants and we don't have any product. So we need to find the products. Here we can recognize ionic compounds because it's made of metal and non-metal. So let's find the ions that they are. So we have Cu, Cl2. Cl is a predictable ion, right? It's in group, here, 7A with bromine, and it's a -1 ion. So it's going to be Cl minus here. Oops, let's rewrite this properly. And then the Cu here, so we have 1 copper for 2 chloride ions with, 2 times 1 negative charge, so 2 negative charges in total. So that means we need 2 positive charges on the copper to cancel those charges. So it's Cu2+ there. In AgNO3, so we have Ag, and Ag is a predictable ion. It's a +1. It's a transition metal, but it's an exception. It always makes the +1 ion. And the NO3, by now, hopefully you recognize that's the nitrate, and it carries 1 negative charge. So that's the ions we have. And we can see that they can exchange partners because they are in aqueous solution. So they are free to move and exchange partners. So the copper will want to go with the nitrate, and the chloride will want to go with the silver. So let's write the product's formula then. And so we will start with Cu2 plus with NO3 minus 1. So, you know, you have 2 positive charges on the copper, but only 1 on the nitrate. So you need 2 nitrates per copper, right? So let's have it like this. So 2 nitrates per copper. Why? Because the copper carries 2 positive charges and each nitrate carries 1 negative charge. So you need 2 nitrate to make 2 negative charges in total. That will cancel the 2 positive charges on the copper. And so this is, well, we need to find out what is the state, physical state. So for this, we need to go to the solubility tables. And we have, well, we have the nitrate here, and the nitrate makes soluble compound with no exception. So this is aqueous. And then we have the silver, Ag plus, going with the chloride, Cl minus. 1 positive charge, 1 negative charge. So it looks like one of each ion will make this a neutral formula. So that's going to be the physical the formula, AgCl. So let's find out the physical state. We have AgCl. Cl is here, and it's making soluble compound. Oh, but when with any of these ions, and there is Ag plus here, the compound is insoluble. So that means AgCl is insoluble. So S for solid here. So let's see if we need to balance. We have 1 copper on the left, 1 copper on the right. Yeah, let's balance the nitrate first, because that's the polyatomic ion here. 2 nitrate on the right, 1 on the left. So let's make it 2 by having a 2 in front of AgNO3 here. Let's find a new color here. So 2 AgNO3, because we want 2 nitrate on the left, like we have on the right. That changes the number of silver here to 2. So we will need to make it 2 silver on the right by having a 2 there in front of AgCl to have 2 silver. And that balances this dichloride, because you see 2 chloride on the left, 2 chloride on the right. So that balances the chloride. And then copper is still balanced here, 1 on the left, 1 on the right. So let's check. Copper, we have 1 on each side. Chlorine, we have 2 on the left, 2 on the right. 2 silver on the left, 2 silver on the right. 2 nitrate on the left, 2 nitrate on the right. So it is balanced now. So let's write that balanced. And I'll make it the color we use to balance so that we understand those coefficients are balancing the equation. So we need to decide what type of reactions we have here. So I think it's obvious here we have a double displacement, right? Because we had an exchange of ions, and so that is typical of double displacement reactions. What else? Is it so double displacement? It can be any of the acid base, precipitation, or you know, gas evolution, right? Any of these will be a double displacement. And we have 2 ionic solutions in the reactant side and 1 solid on the right side. So that tells you this is a precipitation reaction, right? Because one of the product is insoluble. So that tells you this is a precipitation reaction. AgCl is the precipitate, the solid. And that's all.